Hello everyone, today we're going to learn how to convert between different compounds. Our key question that we're going to try to answer today is what is the general procedure for solving a stoichiometric problem? In other words, how do we switch between compounds? And we actually started to learn this in the last lesson when we talked about mole ratio, because mole ratio is how we go from one compound to another. But stoichiometry is more than just going moles to moles. We have to learn how to go from grams to grams. So that's what we're going to focus on in today's lesson. In a typical stoichiometric problem, there are three kind of steps to do. If you're somebody that likes to take notes, this would be a good place to take notes. The first step is you're going to be given a quantity. Now that quantity can be grams, you can be given atoms, you can be given molecules. Whatever you're given, the first step is to switch that into moles. This is your moles of your given. In order to change to moles of your wanted, which is your other substance, we have to use a mole ratio. And remember that ratio comes from a balanced chemical equation. That's why we learned how to balance equations a few lessons ago. This allows us to go from moles of our given to moles of our wanted substance. So in other words, it allows us to convert from one compound to another. Once you get it into moles of your wanted, you can go to any other unit of measurement related to the mole. So you can go from moles to grams, or moles to molecules, or even moles to atoms. Now we say any unit related to the mole. So remember, there are two that we've learned. There's our mole mass relationship, which is where you have 1 mole over molar mass. Or we have Avogadro's number, which is any of our representative units. That includes atoms, molecules, formula units, and ions. That's 1 mole over 6.02 times 10 to the 23rd, whatever particles you have. Here, this is a diagram that I've actually stole out of the chemistry textbook. It kind of helps give you a flow chart of the direction you should go whenever you're solving these types of problems. Don't get too reliant on this because as advanced chem, you should be able to do this and cross out your units without having to use the flow chart. It is beneficial in the beginning, though, to get you started and used to doing this. First, the G is going to be your given quantity. W stands for your wanted. You can start out by getting grams, or you can start out by getting representative particles, or you can even start at moles down here. You have to figure out where you need to start on this table based on your given. So if you're given grams of something, you're going to start here. If you're given moles, you'll start over here. And then representative particles, that's usually if you are given a molecule or an atom or even a formula unit. Then it tells you your conversions you should be using. So for example, if you start with a molecule, you should first use Avogadro's number to cancel out your units. That gives you moles of your given. Here it shows you would use mole ratio to go from moles of your given to moles of your wanted. And then from there, you have to use your correct conversion to get to, if you want to get to molecules or grams. This problem states, determine how many grams of water are produced in the oxidation of 1 gram of glucose, which is C6H12O6. The balanced chemical formula is given below. Note, I'm going from grams of glucose, and I'm trying to get 2 grams of water. There is no direct calculation that allows you to go from grams of one compound to grams of another. So we have to use stoichiometry. First, you always want to take your given and change it to moles. So here I'm going to take my grams and change it to moles. Notice they've labeled their grams. Grams of what? And that's important to label them because that's what your molar mass is going to be dependent on. Here, to go from grams to moles, they found the molar mass of glucose. From there, you can go from moles of one substance to moles of another by using your mole ratio. That gives me my moles of my wanted. And then I can go to grams of my wanted based on molar mass. Notice over here, my molar mass is 18 because I'm working with H2O. That's why it's so important to label your things. A few things I do want to point out because a lot of people get confused on them. First, if you have moles of and grams together, so you're using Avogadro's number or molar mass, this should be the same compound. Here I have grams and moles. Notice my H2O are both the same compound. The only time you should have a different compound on top versus bottom is when you are working with mole ratio. So here is your mole ratio. It is the only time you should have two different compounds. This is also the only time where you will really have a different mole on top and bottom versus just stating one. Note they got the 6 up here in the formula, and they got the 1 up here in the balanced formula. Here is an already worked out example. It says calculate the mass of carbon dioxide produced when 1 gram of butane, which is C4H10, is burned. The formula is balanced below. Notice you are always going to start these with your given. So here it gave me 1 gram of butane, so that's what you're starting with, 1 gram of butane. Notice I labeled my grams instead of just writing G's because you want to cancel your grams of butane. So that's why my grams of butane is right here. This molar mass goes with the butane. This allows me to cancel grams. Now I'm left with moles because your first step is always get into moles. Well, that allows me to go to moles of a different compound using my mole ratio. So if I want to cancel moles of butane has to go on the bottom. This too came from the balanced chemical equation up above. I want to get to moles of carbon dioxide, so moles of carbon dioxide go on top. I got that 8 from here. This allows me to cancel moles of butane. Now that I have it in the moles of my wanted, we have to convert it to moles of my wanted to mass of my wanted. So I'm going to use molar mass. Notice moles of carbon dioxide need to go on the bottom in order to cancel them, and that leaves me with grams of CO2. Note, the molar mass that I calculated is the molar mass of CO2. Then you guys can go ahead and solve this. 1 divided by 58.123 times 8, because it's on top, divided by 2 times 44.009. You're going to get a long answer, but since I started with 3 sig figs, my answer should be rounded to 3 sig figs. So here, 3.03 grams, and make sure you include your unit, CO2. Here's another example where we're going to practice. It says calculate the number of grams of ammonia, which is NH3, produced by the reaction if 5.40 grams of hydrogen is reacted with excess nitrogen. The balanced equation is located below. So again, you always start with what you're given. You are given 5.4 grams. And I'm going to write 5.40 so I don't forget my sig figs. Now this is grams of hydrogen, so grams of H2. First thing, no matter what you are given, get it into moles first if it is not already in moles. So I need to go from grams to moles, and the only way to do that is to use molar mass. So grams for every 1 mole. Notice this is grams of H2 because I want to cancel it, and moles of H2. They should be the same compound. Here I have 2 hydrogen, so if I do that on the periodic table, it's 2.0158 for every 1 mole because it's grams per mole. That allows me to cancel out grams of H2. From there, I can go from moles of one compound to moles of another using mole ratio. So note that I want to cancel out my moles of H2, so it needs to go on the bottom, opposite. And I'm trying to get to moles of NH3. So that's going to go on top. The numbers out here come from a balanced chemical equation. So if I look at NH3, it's going to be a 2. If I look at H2, it's going to be a 3. That allows me to cancel out moles of H2, and I'm left with moles of NH3. But my problem is asking me to get to grams of NH3. So to go from moles to grams, we're going to use molar mass. So here, make sure you are canceling your units. Moles of NH3 have to go on bottom, and grams of NH3 has to go on top. When you find the molar mass of NH3, you get 17.0307. And here, mole, since I'm working with grams per mole, this is 17 grams for every 1 mole. Then you guys can go ahead and solve out, and you get 30.4149865. I can only have 3 sig figs because of my 5.40. So 3 sig figs is 30.4. My unit is grams. In order to get your full points, remember, I'm asking grams of what? NH3. If you don't specify, that could be grams of H2 or N2. So you need to be specific. Another example tells you to calculate the mass of oxygen consumed when 1 gram of butane is burned. And of course, it gives you the formula that we saw in the previous slide. Note, you always start with what you're given. 1 gram of butane. So C4H10. In order to cancel out grams, it's got to go on the bottom. And this gram has to be of butane to cancel that. And this one's going to be moles of butane. So if I find the molar mass of this formula, you're going to get 58.123 for every 1 mole. This allows me to cancel my grams. Now that I have it in moles, we can use our mole ratio. So for moles of C4H10, in my formula, I have 2 of them. I want to get to oxygen, which is right over here. So oxygen's 13. So this cancels out my moles of my butane. I have moles of O2, but I want mass, so I need to use my molar mass. So for every 1 mole of oxygen, my molar mass of oxygen is 31.998, I believe. Yep, grams of O2. This allows me to cancel these units because they're opposite, and it leaves me with what I wanted. Note, 1 divided by 58 times 13 divided by 2, because it's on bottom, times 31. When you guys solve that, you get 3.5783, etc. Because these zeros are at the end and there's a decimal, there is 3 sig figs for this number. So 3.58 grams of O2. Now, we said that you don't have to only start with grams. You can also go to molecules, atoms, formula units. So let's do an example where we are working with molecules here. This question reads, how many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis, according to the balanced equation below? Always start with what you're given. Here, you're given 29.2 grams of H2O. If I want to cancel out, I want to get to moles first. Grams, you have to use molar mass. So you want to put grams of H2O on the bottom for moles of H2O. Note, they're the same compound. So when you calculate this, the molar mass of H2O is 18.0148 grams of H2O for every 1 mole. That allows me to cancel. Here, now that I have it in moles, you can do your mole ratio. Moles of H2O, and I want to get to moles of O2. So here, I have 2 H2O and only 1 O2s. Then, you wouldn't do molar mass because I'm not trying to find grams. I'm trying to find molecules. So we have to make sure we're canceling and going the right step. If I have moles of O2 to cancel them on the bottom, molecules of O2 has to go on the top. And we know that Avogadro's number is used to convert to molecules. So Avogadro's number over 1 mole. This allows us to cancel moles of O2. When you solve this across, you get 4.878877, etc., times 10 to the 23rd. Based on our beginning number here, we can only have 3 sig figs, so 4.88 times 10 to the 23rd molecules of O2. Here is our last problem. I want you to pause this video and see if you can solve it, and then unpause it and see if you get it right. Now that hopefully you've tried to solve it, we are given 54.1 grams of H2. In order to cancel this, we're going to use our molar mass. So 1 mole of H2, there are 2.0158 grams. Now that I've canceled grams of H2, I can go to the other compound using molar mass. So notice that for every 2 moles of H2, the 2 comes from the balanced equation, there are 2 moles of water, again from that equation. This allows us to cancel moles of H2. And then note, we're going to a molecule now, so we need to use Avogadro's number. So for every 1 mole of H2O, there are 6.02 times 10 to the 23rd molecules of H2O. When we solve this, you get 1.615646 times 10 to the 25th. 25th. Again, you can only have 3 sig figs because I have 3 sig figs in the beginning, so 1.62 times 10 to the 25th molecule of H2O. So how'd you do? Couple things to note before I sign off. Remember, these should be the same compound. These ones should be the same compound. The only time you can have a different compound is when you're working with mole ratio. If you have any questions, please make sure that you email me or you come in for help. Otherwise I hope you guys have a great day.